Hello, Precalculus students. Today's notes are on an entirely new unit on trigonometry. So today we'll be talking about the unit circle, which you had some experience with in Algebra 2, but hopefully through our work in Precalculus, it makes a lot more sense to you, and hopefully it's a lot more useful to you. So first example says convert the following degree measures to radians and radian measures to degrees. So these two on the left are degree measures. We're going to convert those to radians. These two on the right are radian measures. We're going to convert to degrees. So up till now, so thinking about your geometry days, you measured angles with degrees. And you know there's 360 degrees all the way around a circle. Now we're going to talk about a different measure, which is radians. And actually, radians make a whole lot more sense. So what a radian is, so for example, thinking about a circle, I'm just going to draw a circle with radius 1 centered at the origin. The angle measure that you're measuring here in radians is the same as this distance around the circle. That's what a radian is. So radian has to do with this distance around the circle. All the way around the circle is 2 pi. Just like here, all the way around the circle is 360 degrees. And let's actually think halfway around the circle. We know that 180 degrees is the same as pi radians. Now, if you know that, you know everything you need to know to convert radians to degrees. Now, I know in Algebra 2 you might have learned sometimes you multiply by 180, sometimes you divide by 180, but really all you need to know is this fact. Now, since those two quantities are the same, this quantity here is equal to 1. And so is this quantity here. This is also equal to 1. So let's just think about this. We want to take 45 degrees and multiply by one of these quantities here. And we want the degree sign to simplify so it is gone. So if we take this quantity right here and multiply it by 45 degrees, multiplying top times the top, bottom times the bottom, these degree signs will simplify and be gone. So we'll be left with the quantity 45 pi over 180, which if you simplify this fraction here, you'll get pi over 4. Now here's another way of thinking about it. 45 degrees is this angle right about here. That angle is a fourth of the way to making a straight line. So it's 1/4 pi, 1/4 of that straight line. Okay, same thing down here. Let's take that 1080 times pi over 180 degrees. And again, the degree sign will simplify and be gone, so you don't have that anymore. So if we multiply top times the top and bottom times the bottom, we get 1080 pi over 180, which if we divide those quantities, we get 6 pi. So this angle measure here would be 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. It's actually 3 times around the circle. We know 2 pi is twice around, 2 pi is around the circle, so 6 pi would be 3 times around the circle. Okay, same thing here. 3 pi over 4, we need to multiply by a quantity that's equal to 1. So I'm going to just grab this here and multiply by this quantity. And if you think about it, when we multiply by this quantity, the pi will simplify and the degree sign will remain. Well, that's exactly what we want to happen. And if you multiply top times the top, bottom times the bottom, well, I'm going to simplify a little bit first. As I multiply, this will be equal to 135 degrees. And here's another way of thinking about that. 3 pi over 4 is 3/4 of the way to a straight line. Okay, so it's 3/4 of 180, which is 135. Same thing down here. We can multiply by 180 degrees over pi. And really, this is 5/6 of the way to 180, which is 150 degrees. So make sure you can not only just convert between radians and degrees, but understand what a radian measure is. For example, when you visualize 45 degrees, most of us can visualize about how big that angle is. We should be able to visualize pi over 4, 3 pi over 4, 5 pi over 6 the same exact way. Okay, let's talk about our second example. Second example, determine two coterminal angles for the given angle. Well, I'm just going to sketch this angle first. And I'm not going to convert it to degrees because we should be able to visualize 2/3 pi means 2/3 of the way to a straight line. So we always start with this x-axis here, and we always measure counterclockwise. So 2/3 pi would be right about here. So that's this angle here, and I'll mark it on my diagram, 2/3 pi. Now, coterminal means an angle that goes around this set of axes in either direction but ends at the same place. Coterminal means with the same ending. Okay, so if we had some angle that started at the same place, went all the way around the circle, and then came back to that same angle measure, that would be a coterminal angle. So to find that, we could say, okay, all the way around the circle is 2 pi plus that 2 pi over 3 that we had here. Okay, and if we add these quantities, I'm just going to write this in a different form, 6 pi over 3 plus 2 pi over 3. We get another coterminal angle, 8 pi over 3. And there would be one possible solution. Well, if you think about this, we could continue to add 2 pi or 6 pi over 3. So 14 pi over 3, 20 pi over 3. Any of those quantities would give you a coterminal angle. Now, another way to find a coterminal angle is to say, well, what if we went in this direction? Because we can have negative angles that actually are measured clockwise. It ends in the same place. Well, if you went all the way around the circle the other way, that would be negative 2 pi. And then from that, if you added that 2 pi over 3, well, again, let's think with a common denominator here. You would end up with negative 4 pi over 3. Which, if you think about it, we're going negative 4/3 of the way past this line. So 3/3 would be to this line, 1/3 more. There's another coterminal angle. There's an infinite number of coterminal angles. This is how we can find 2 of them. Okay, let's move on to a third example. So this example reads, if sine of theta equals 5 pi over 3, and theta is in quadrant 1, find the values of the 6 trigonometric functions of theta. Now I tell you what, in almost everything we do in this unit, it's much easier to visualize it if you can make some kind of diagram. So let's do that. So I'm going to draw a couple axes. And it's talking about theta's in quadrant 1, so I know it's going to be in this top right corner. So I'm going to draw a right triangle here. I'll put theta down here at the origin. And sine, we know SOHCAHTOA tells us sine is opposite over hypotenuse. And from those two, we can use the Pythagorean theorem to find this missing side. Now that we have this sketch, this problem is actually relatively easy. We're being asked to find the sine of theta, the cosine of theta, the tangent of theta. There's your 3 main trigonometric functions, but we also have 3 others that we're talking about. We have the cotangent of theta, the secant of theta, and the cosecant of theta. Well, SOHCAHTOA tells us that the sine of theta is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So those first 3 we're usually pretty good on. Now, the next 3 are reciprocals of the first 3. And we can line them up like so. So if we know the tangent of theta, we also know the cotangent. It's 12 over 5. If we know cosine, then we know secant is 13 over 12. And if we know sine, then we know cosecant is 13 over 5. So there are the 6 trigonometric functions of theta, but it all starts with the diagram. If you make your diagram and it makes sense, coming up with these answers is relatively easy. Okay, let's shift gears a little bit. I want to take you back to your geometry days. Now in geometry, you talked about 2 special right triangles, and here's one of them. So this special right triangle, 45, it's actually a 45, we'll put another 45 degree up here, 45, 45, 90 triangle. Let's see if we can come up with the side lengths of these triangles. So I'm just going to call this dimension here 1 unit. Now, since this is an isosceles triangle, these 2 angles are the same, that means these 2 sides must be the same. And since those sides are the same, we can mark them both 1, and then we can use the Pythagorean theorem, 1 squared plus 1 squared equals 2. And the square root of that would be this quantity right here. So there's the dimensions of a 45, 45, 90 right triangle. Now, for what we do later on, we want this hypotenuse, we want this dimension to be 1. So I'm going to divide every side by the square root of 2. That'll just make this triangle a little bit smaller. And I'm going to erase what I've got up there and just rewrite these quantities a little bit differently. So instead of writing square root of 2 over 2, I'm going to write this as 1. Instead of writing 1 over square root of 2, let's rationalize the denominator. And we can write that, let me get rid of what's here. We can write that as the square root of 2 over 2. Likewise, this quantity here is the same thing. So again, we say square root of 2 over 2. Okay, if you can come up with this special right triangle, you can fill in about half of your unit circles. So keep this right triangle in mind. Now that we've got that right triangle, let's talk about our other special right triangle from geometry. This is our 30, 60, 90 special right triangle. And again, we don't have any measurements here, so I'm just going to put a 1 over here on this shortest side. And we learned in our geometry days that the shortest side times 2 is equal to the hypotenuse. We also learned the shortest side times the square root of 3 is equal to this medium side. Now again, we want this hypotenuse to be equal to 1. We'll see why in just a little bit. So let's divide every one of those dimensions by 2. If we do that, that gives us, and I'll just get rid of this 2 and rewrite it, that gives us the following dimensions. Now, if you can come up with the dimensions of these two special right triangles, you can fill in this entire unit circle without having to memorize, without having to do a whole lot of work. Here's how. So let's talk about our 30, 60, 90 triangle first. So 30, 60, 90 triangle will fit perfectly right here. How do I know it fits perfectly? Well, we know that the hypotenuse is 1 unit long. Unit circle, it's called a unit circle because it has a radius of 1 unit. Now these dimensions here, we know this one here is square root of 3 over 2. We know this one here is 1/2. So when we're coming up with these points around the unit circle, what we're really doing is saying, what's the coordinate of this point here? Well, it's square root of 3 over 2 to the right and 1/2 up. And there's that point. Now, likewise, we could put a 30, 60, 90 right triangle on its other side right here. We have the same dimensions, just switch the x and y. So I'm just going to write that as 1/2 and square root of 3 over 2. Okay. Let's pull in that other special right triangle now. Now the other special right triangle, that 45, 45, 90 triangle, if we put it in here, it would fit in this spot right here. Again, the hypotenuse is 1 unit. This side down here would be square root of 2 over 2. Likewise, this side over here. That gives us this point here has an x, y value of square root of 2 over 2, comma, square root of 2 over 2. Okay, now that we've got that, everything else just flows from there. So these points over here in the second quadrant are in the exact same spots. We just have some negative dimensions because we're counting to the left and up. So this green value I have over here is going to be the same value except we're going left, square root of 2 over 2, and then up, square root of 2 over 2. And likewise, we can get all these points here the same way. This one goes left and down. So those are both negative quantities. This one here goes right and down. And then we can take those other points, the ones I've got written in black, and do the same thing. So this one here goes left square root of 3 over 2 and up 1/2. This one here goes left square root of 3 over 2 and down 1/2. And this one here goes right square root of 3 over 2 and down 1/2. So I will fill in the rest of these points by thinking, am I counting left or right, and using that to tell me, are these positive or negative quantities? So notice, no need to do a lot of memorization here. If you understand those special right triangles, which you learned about in your geometry days, you can come up with all those points. Now there's a couple points not labeled that we should get. So this one here is -1, 0. This one down here is 0, -1, because they're 1 unit away from the origin. Okay, now let's get a little bit more labeled on this unit circle. So let's get some angle measures as well. So we've got these points labeled on here, so let's get angle measures, and I'll get these in a different color. So that green angle I've got marked there, that is at 45 degrees, which is 1/4 of the way to a straight line. So I can write it as a degree. I can also write it in radians. Now if that's 1/4 of the way, right here would be 2/4 or 1/2. So we know this 90-degree angle is the same as 2/4 or 1/2 pi. This next green point over here is going to be 45 more degrees, or another quarter, so now we're talking about 3/4 pi. And then this point over here is going to be 180 degrees, which is like 4/4 or just pi. And so every one of these points, and I'll mark them in blue, is 1/4 of the way to a straight line. So if we add 1/4 to each of the previous quantities, we should be good. So 1/4, 2/4, 3/4, 4/4. Here we have 5/4, which is the same as 225 degrees. Here we have 6/4, which is the same as 270 degrees. And down here we have 7/4 pi, which is the same as 315 degrees. Okay, last I'm going to mark our remaining points. Notice our remaining points are every 30 degrees. So we could mark these in degrees. We can also mark them in radians. I'm going to go around in degrees first. So here's 30 degrees, 60 degrees, we have 90, and we now have 120 degrees, 150 degrees, we already have 180. Here's 210 degrees, here's 240 degrees, we already have 270. Here is 300 degrees, here's 330 degrees, and all the way here is 360 degrees or 0. Now, all those degree measures in red that we just marked, we can also measure in radians. So 30 degrees, that's 1/6 of the way to a straight line. So here's pi over 6. Here's 2 pi over 6. Here is 3 pi over 6. Here's 4 pi over 6. Here is 5 pi over 6 radians. 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6 would be this 2 pi, or 0 radians. Alright, so there's our unit circle. Now, we're going to learn about how the unit circle is really a tool for us. It will help us simplify and do problems easier. At this point, we just need to fill it all in so that we are able to use this as a tool. Okay, now that we've got that, I've got an assignment for you to look at on pages 265 and 274. So see what you can do on this assignment. When you're done with this, we can move on to our next lesson.